Okay, wonderful. We have started the recording. We're recording this meeting. I have the chat window set up over here. So all systems are go. Okay, this is just a quick reminder. As you know, in our last lecture, we discussed some issues that relate to the current homework assignment. Okay, homework number 10. There is an investigation of this angular momentum sphere, and this is a drawing of the angular momentum sphere. As you know, there's a much better picture in the lecture notes, and I have indicated in the homework 10 document, I provide a pointer to a certain installment of lecture notes where we have a wonderful angular momentum sphere created by Jerry Marsden and others. These are some folks in at the time, Berkeley Mathematics Department. Okay, so we talked about this last time. This is a two-dimensional phase space. Remember, phase spaces are always even dimensional. Two-dimensional phase space, we talked about these curves, the streamlines. Of course, the total mechanical energy is constant along any one of these curves. And we talked about the simple pendulum. Very similar structure. We do have the separatrix, again, the dashed line. That is a curve. Of course, the total mechanical energy is a constant along that curve, shown as a dashed line here. All the other curves are solid lines. Interesting things, it takes infinitely long to reach this critical point if you're approaching it, because what that means is the pendulum has precisely enough energy to reach that position where it's perfectly balanced upright, okay? So it asymptotically approaches that position where it's perfectly balanced, but it slows down as it approaches the vertical. Because we have precisely enough energy to get there, it slows down as we approach the vertical. And in fact, it would take infinitely long to get there. It gets slower and slower as we approach that. So you have this structure at the critical point where two of these manifolds, these are one-dimensional manifolds, they approach, right, the flow. Remember, I drew this little arrow here to indicate on that curve, the flow is clockwise, and that's true for all these other, there's a family of curves here. And by extension, on the separatrix, the flow is like so. I'm indicating, wait a second. I was indicating with the mouse pointer, I need to indicate over here. I can use the mouse pointer when I'm doing other things with the zoom, but for this particular thing, I must indicate with the pen here. This arrow shows the sense of rotation for this curve, which looks like an ellipse. It's not exactly an ellipse, but it looks like an ellipse in the sense that it's round and it's not a circle. And it has some symmetries. Okay, so that tells you there's a vector field here. And it's this vector field that, okay, I do see there is a comment in the chat window. I will address the comment in the chat window in just a moment. Just wanted to make a few remarks for the current homework assignment, right? Homework number 10. We want to really appreciate the existence of a vector field on phase space. That's the crucial thing. Phase space has been underlined here. The concept of phase space is crucial to the Hamiltonian formulation of mechanics. This is the phase space for the simple pendulum, and we're showing streamlines here. The streamlines are everywhere tangent to the vector field. What is the vector field? Well, the vector field is precisely what Hamilton's equations give you. Hamilton's equations give you Q dot equals something, right? Obviously, it's a partial derivative of the Hamiltonian, and P dot equals something. We don't need to write down the formulas because it's this structure here that is important right now. The evolution of the system, okay? This is the general notation with our generalized coordinate Q and a canonical momentum P. The structure of Hamilton's equations have first order time derivatives equaling a function defined on phase space, and so that has the structure of a vector field. These diagrams help us to understand the vector field. I've only drawn one thing that isn't even reminiscent of a vector. That's this arrowhead showing you the sense of rotation of that curve, but I didn't even draw the full vector. If I drew the vectors, it would be a pretty busy diagram. There'd be arrows everywhere. So often it's useful to draw the streamlines. These are curves that are everywhere tangent to the vector field. the evolution of the system will follow one of these curves because the energy is conserved, right? These are curves of constant mechanical energy, and so the evolution of the system follows these curves. The same remarks apply to this sphere. This sphere has been intensively studied and celebrated. It's a wonderful sphere. The same remarks apply here. This two-dimensional phase space, it has the structure of a phase space, and we're going to say some more words about that in today's lecture. But let's appreciate that these curves have constant energy. We talked about the kinetic energy. It's very similar in form to the square of the angular momentum. You just have some multiplicative prefactors that are constants, okay? And when we worked out the intersections between the spheres, right? This equation gives you a sphere, and this equation expresses the constancy of the kinetic energy, which is the total, right? The kinetic energy is the total energy here for this system. We got these nice curves. Similar remarks apply to the separatrix. It takes infinitely long to approach this critical point along two of these arcs that come in, and then you will asymptotically grow, the error grows asymptotically as you move away from the separatrix. Again, if you're on this critical line, I should say separatrix, which goes to the critical point. For curves, generic curves which go near this intermediate axis, the system moves very slowly. And that's the key to understanding the dancing T-handle, etc. And then the system moves quickly elsewhere. So this is kind of an overview of what we talked about last time. I did post this, a copy of this sheet of paper. I posted it in the homework 10 folder a short while ago, maybe 10, 20 minutes ago. I uploaded it because this discussion is relevant for problem number 2 on the homework assignment. And what we want to do is appreciate the geometry, right? We're talking about various abstract spaces here and vector fields defined on these spaces. So that's the structure. Again, we mentioned yesterday, to truly appreciate what's happening here, right? We have a remark. I put a remark in the homework 10 that we're computing a vector field that's tangent to this sphere. And the crucial thing is we're computing it using first order derivatives of the energy. And then there's a certain operation which turns those derivatives into a vector field. Now that operation, in this case, involved a simple cross product. Okay, that's a very welcome surprise. The cross product is related to something called the symplectic structure. So to truly go into detail, you'll have to take Physics 205. So promise me you'll take Physics 205 and really get into this stuff. But later today, we'll say some more words about the Poisson Bracket, okay? For this homework problem, number 2 on the current assignment, it's kind of mysterious how this cross product occurs, and we'll just have to accept the big picture. The big picture is we computed first order derivatives of the Hamiltonian, and then we went through a certain procedure which gave us a vector field. Okay, so that's the big picture. And again, I did post this in the homework 10 folder. Okay, now I have a question in the chat window. Let me have a look at this question. Update the syllabus with the grading distribution. Okay, and okay, grading distribution. Let me address that. Traditionally, this course is graded on a curve, and traditionally, 35% of the students would get an A. The top 35% of the students get an A. That, when we say that, we mean that's the union of A pluses, A's, and A minuses. For this kind of remark, we call all of those A plus, A minus, we call those the A's. 35% of the students get A. The next 40% get B's, okay? We don't have to give D's and F's, but sometimes we must do that. Anyways, so traditionally, that's what is done. We have a specific distribution. Now, because of the COVID pandemic and the fact that we are doing remote instruction, there will not be a distribution, okay? I cannot tell you a certain percentage of the students will get A's. The reason is because we face a big problem with academic dishonesty, okay? We cannot really do much about academic dishonesty. And it would be very unfair if cheaters got a better grade, and if we were using a distribution, then a cheater going up in terms of the grades will cause an honest student to go down. That's not acceptable. So the situation here for remote instruction is that cheaters will get a better grade. There's nothing we can do about that, but we cannot have them lower the grade of an honest student. Therefore, there's no distribution. We must evaluate every student's work and look for mastery of concepts, okay? So this is actually quite a burden on the grading team. It requires more effort to do this. Traditionally, we would just grade the exams using whatever scale, and then the top 35% of students get an A. We can't do that now. We have to analyze every student's work and ask if they have mastered the concepts. Okay, so that's about enough. You mentioned, yeah, okay. I mentioned, we did talk about this earlier. For your earlier work on midterm number 1, okay, following a very careful analysis and a very careful structure to the grading scheme, ultimately, we will have some system where we assign letter grades, but we cannot state right now the details of the numerical their thresholds. Okay, that's very difficult. It's likely that we're going to stay with this number of 70%, but that number is not yet set in stone. Okay, so I appreciate you mentioned you're going to be attending other schools. You need to submit a syllabus. Okay, yeah, so let's talk some more offline. There are some nuances and we welcome your input, but we're facing great difficulties here with remote instruction and assigning letter grades fairly in the world of remote instruction. Okay, so for today's lecture, you know, I've made some remarks now on the basic philosophy. The overall goal is we must ensure that students get grades, the honest students get grades that they deserve, okay? And how to do this is very difficult. So we'll talk some more, and yeah, we'll update the syllabus. So yeah, great. So we'll have, yeah, excellent remark. I appreciate your feedback. And as always, we welcome all students' feedback on this difficult question. So yeah, as you pointed, the syllabus should be updated to reflect the philosophy of how we determine grades and how we examine students' work and look for mastery of concepts. Okay, great question. Okay, so now let's continue with today's lecture. So I'll get this piece of paper here. Okay, so we've got Thursday the 6th, all right? Let's talk about a few things. First of all, let's talk about the reading assignment. Okay, the reading assignment, here's the situation. It's most important that you read section 12.9. So that's section 9 of chapter 12. Okay, that's important. Homework number 11, that's the last homework for our course. Homework number 11 will be based on this section. So this is important that you read this, okay? This section is not on the final exam. In fact, none of chapter 12 is on the final exam. Okay, so this is the structure of the reading assignment. This is our last reading assignment for the course. And notice the structure. It's very important that you do number 1 here. Okay, we need to read section 12.9. Fascinating section. We're talking about chaos. Ideally, you would also read the rest of chapter 12. Okay, but I understand you're busy with a lot of things. So perhaps you can read that quickly and just get a feeling for the wonderful world of chaos, fascinating developments in recent decades. Okay, a couple hundred years ago, they were not so concerned with chaos. They didn't realize the importance of chaos. Nowadays, we realize that chaos, in fact, is the most generic behavior. Most systems are chaotic. It's very special that we have the so-called integrable systems. things like the Kepler orbits, wonderful orbits that close on themselves. That's a very special state of affairs. And historically, people focused on these special problems because they were easier to solve. The general case, for example, the double pendulum, it's a chaotic system, and you cannot write down a simple formula for the solution. All right, that's kind of the generic behavior in mechanics. Chaos is ubiquitous. There's chaos everywhere. There's typically a sea of chaos, and then we have these islands of stability. So we'll talk about the sea of chaos and the islands of stability to appreciate that really mechanical systems in general are more difficult than these integrable problems that we've been solving. Things like the Kepler problem, where you have the orbits of planets around the sun, etc. Those problems, in some sense, they're artificially simple because you have all these conserved quantities. You have the angular momentum, and you remember the Runge length vector. The Kepler problem has conservation of total mechanical energy, conservation of the angular momentum vector, and there was another vector, it's not in Taylor, the so-called Runge length vector. This is logically distinct from the angular momentum vector. It's a fundamentally different conserved quantity, and it's responsible for this very high symmetry, the closed orbits, etc. So again, these problems with high symmetry, and you see this in the non-relativistic Schrodinger equation when you start doing quantum mechanics, the hydrogen atom has, in non-relativistic quantum mechanics, has tremendous degeneracy. The energy levels depend only on the principal quantum number. They don't care about the angular momentum quantum number L. They don't care about the magnetic quantum number M. They depend only on the principal quantum number. Of course, when you do more detailed quantum mechanical analysis, you get some other structure. You have the Dirac equation, you have the hyperfine splitting. It gets progressively more sophisticated. All right, so yeah, the big picture is it would be nice if you could read chapter 12, at least skim through it to appreciate the wonderful world of chaos. This stuff is not on the final exam, but this first item is important for our last homework assignment, and this does involve computer programming. And that's why the tool of the modern era, the computer, is really something that should be a big part. It should play a prominent role in your physics degree. We need to bring in the computer programming. It's a modern skill. It allows you to see the chaos that you could not see with the traditional methods of a couple hundred years ago, okay? So most of the result in Taylor's book, other than chapter 12, we have systems where we can kind of write down formulas for the answers, stuff like that. That's rare. It's rare that a real problem can be written like that. Even the problem of the Earth, Moon, and Sun, the three-body problem, you can't write down a simple solution for that. Okay, so what we'll do now is proceed. We're going to look at some more topics in chapter 13, and then we will go into chapter 12. Today, Thursday, this is the last lecture of week 7. Next week is week 8. It's the last week of the course. And we have Monday, Tuesday, Wednesday, Thursday. Thursday's the final exam, so we have 3 lectures next week. Okay, so next week we'll talk about chapter 12 in lecture, and also we'll be doing some review sessions. Okay, so reviewing for the final exam is important. Now notice what we have been doing here in chapter 13. We've been looking for every opportunity to review foundation material. And let's do that once again. We want to seize upon any opportunity to review foundation material that you need for the final exam. Here's an example. Okay, let's review what we did in chapter 8. Chapter 8 is crucial, right? Chapter 8, the Kepler orbits. This is one of the crown jewels of classical mechanics. The ability to take this inverse square gravitational law and show that the result includes these elliptical orbits, the special parabolic trajectory, and the hyperbolic cases. That's an amazing achievement. Remember the 6 degrees of freedom, 3 degrees of freedom, 2 degrees of freedom, 1 degree of freedom. This progression, systematically using symmetry to reduce the problem, using mathematical tools to reduce the complexity of the problem and ultimately solve it. That's what we've been talking about. In our last meeting, we talked about something similar, right? We observed if you have a Hamiltonian in a 3-dimensional space, and if you're interested in the shape of the trajectory, okay, the key word there, shape, that is a direct connection to what we said about the elliptical orbits. Okay, if you're interested in the shape of the trajectory for a generic 3 degree of freedom problem, then you can reduce the complexity from a 3 degree of freedom problem to a 2 degree of freedom problem with a time, and that's a quote, time dependent Hamiltonian. Really, when we say quote, time dependent, we've chosen the z-axis, we've arbitrarily spoiled the symmetry, we chose the z-axis, we singled out the z-axis for special treatment, we consider the z coordinate as our independent variable, and we'd like to solve for x and y as a function of z. That gives us the shape of the trajectory. With that information, you can draw a picture or make a three-dimensional model of the trajectory. So that's the shape. We don't get information about how quickly or slowly you move along that path. Okay, so that's an example of using mathematical skills. And we did this at the end of our last lecture to reduce the level of difficulty of the problem. Okay, so again, chapter 8, foundation. Let's talk about how chapter 8 relates to the current homework. We always look for these opportunities to make connections. Chapter 8 relates to the current homework, and also it relates to some of our optics discussions. Remember, those optics discussions were optional discussions. You won't see them on the final exam. They're not in the book. Nevertheless, they were very profitable. We learned a lot and we saw some interesting connections. So here we go. Let's look at the following. We're going to turn back the hands of time. Okay, here we want to make some connections. We had our first optics discussion. What was the purpose of that discussion? It was a great opportunity to see how the Hamiltonian formulation could be used, right? Well, the collection of 3 optics discussions. Remember, the first optics discussion could not be formulated using a Hamiltonian. That was a useful learning experience right there. It reminded us what's involved in creating a Hamiltonian. And we saw it was impossible to create a Hamiltonian for the first optics discussion. This was a springboard into the second and third optics discussions. Okay, let's connect that with the current homework. Okay, we've got homework 10, the current homework assignment. We've got problem 13.7. That's page 551. Perhaps you've noticed my writing's getting smaller because I have to squeeze a bunch of stuff in here. Okay, this is going to be a 3-way comparison. We're comparing this, and one more thing. Let's look at chapter 8. Let's compare this with chapter 8. It's useful to see the universality, to see the interrelatedness of all things. Chapter 8, let's look at equation 8.39. All right, page 306. Okay, so you see it's going to be an exciting 3-way comparison. Okay, yeah, it's an exciting 3-way comparison. What we're doing here, we're going to focus our attention on some foundation mathematical skills, important stuff that's very fundamental to the course. Okay, so here's what we're talking about. And again, you need this for the current homework assignment. To appreciate what's going on here with this problem, you need to be able to transform differential equations. Okay, so remember what we did in our first optics discussion. We had a parameterization. Okay, we had a mapping, and the way we often like to write these things, we had the position in a 3-dimensional space. So this is our familiar R vector That's x comma y comma z. It's a special vector. It holds a special place in our hearts. R is a function. Okay. This is the way we like to express functional relationships. You know, functional relationships are so fundamental to our course. And what we're saying here is we have a parameterization. This is a function. You provide a single value lambda, and this mapping gives you a point in space. Okay, so that means there's a lambda axis. Here's a lambda axis. In particular, we chose two. Here's a lambda axis. Here's the origin. There's 0. Here's +1. We're going to use this interval. Okay, so this is a mapping to a three-dimensional space like this. Okay, you have this particular discussion was for ray optics. So suppose you have a slab of glass with a non-uniform index of refraction. A ray of light might do something like this. If this is a slab of glass with a truly non-uniform index of refraction, that could happen. Maybe you're doing astrophysics, you've got some interstellar dust cloud, and you know the index of refraction will vary as a function of position. It'll be fairly close to 1 because these clouds are fairly thin, right, in terms of their density. Nevertheless, you have refraction taking place. So this is a mapping, a typical value here. Typical value, here's a typical lambda value. It gets mapped to some point in space. So that's a parameterization, okay? We talked about R prime. Okay, so this is important to understand here. These skills that we used in the first optics discussion, these skills apply directly to other parts of our course, parts that you are responsible for, okay? Well, let's talk about homework 10 here, problem 13.7. In chapter 8, there are fundamental skills here that are present when we transform differential equations, okay? And what happened in our first optics discussion, we had a Lagrangian, we got an equation of motion. Okay, so you see I've written it like this, the capital cursive L representing a Lagrangian. This arrow represents logical implication. This is our abbreviation for equations of motion. So this collection of 5 symbols really encapsulates one of the most fundamental things about our course. If you have a Lagrangian, you use it to get an equation of motion. That's a differential equation you must solve. And in this case, we got the generalized Snell's law, okay? So in this case, what we did, okay, in this case, what we did is the following, and this is the crucial thing to understand. This construction here occurs certainly in chapter 8, and something related happens in chapter 10. We must appreciate the foundation concepts that occur here in chapter 8 and in chapter 10, homework 10, chapter 10. Let's appreciate the foundation concepts that occur, and it's this equation here. So notice we used lambda as the parameter of evolution. Ordinarily in mechanics, we have the time t. We are searching for the solution, the position of a particle, for example, as a function of the time t, and the time t is the parameter of evolution. For this optics discussion, we used an arbitrary parameter lambda, okay? It turns out the arc length was not suitable for this portion of the discussion. Later, when we got the equation of motion, we transformed back to arc length. Okay, so I'll include that here as a remark. Lowercase s equals arc length we like to use lowercase s as arc length. The same thing is true here. Is it not true? And I quote. Here I go. We're going for page 551. Let's appreciate what's going on page 551. Let's appreciate we have a document camera, and all I have to do is turn to page 551 and put it on the document camera, like so. Okay. We do have a little bit of a collision here. We have a collision. I'm going to scoot over the laptop. It's so heavy. Okay. I think we're okay. Yeah, that's page 551. Here's problem 13.7. As you know, we have the roller coaster. Okay, now it's a little hard to see, but that's an MS double dot. You see the little S there? S is the distance measured along the track. This is crucial. It says it there in the text. The lowercase s is the distance measured along the track. All right, so you see, same thing here. S equals ditto. When I say ditto, the words that were used in that problem, 13.7, were S is the distance measured along the track. That's synonymous with this statement here, arc length. Okay, in geometry, we speak of the arc length. It's distance measured along a curve. Okay, so there you have it. Now, in this homework problem, we're going to talk about S double dot. Okay, let's compare and contrast. We're going to make some comments on the S double dot. What is S double dot? Well, you know the dot is our special physics notation for this DDT operator, the total time derivative. Okay, so what we're doing here is we're changing, let the record show, in this case, we're changing the dependent variable. Right, because we have two things that we're talking about. Okay, rewrite this as an equation for X double dot. There are two things that we're interested in. We have a function X of t, and we have a function S of t. Okay, so let's appreciate in this problem, and I'm going to emphasize, and I'm going to truly emphasize with the red color. For this problem, we're changing the dependent. Now that didn't, you know, it's so nice and red on the paper, and then I look at the document camera, it's a far cry from being red. Okay, that's changing a dependent variable. Here, we're changing the independent variable. Okay, and you know I must underline okay. Okay, now let's talk about chapter 8, and then we're going to have a grand finale here where we really appreciate the differences and the similarities. Okay, obviously a similarity here. We're talking about arc length. This lowercase s, for some reason, just did not look very good. That's a lowercase s, lowercase s. All right, let's talk about page 306. This is very important for our understanding of Remember those elliptical orbits, the parabolic path, et cetera, and so forth? The hyperbolic trajectory. Page 306 sets the stage. 306. This one's an even number. And you know what that means? I got some different constraints as I put the book on the document camera. Okay, page 306. What are we doing here? We're transforming a differential equation. Here's our differential equation. You see the r double dot, okay? This is crucial. So we have equation 837 with an r double dot. Right? This is one of the first things to observe. Now we're going to change the independent variable and we're going to change the dependent variable. So change both. Okay, so lots of red ink. Here comes a whole bunch of red ink. Okay. So we change the independent variable. What do we have here? The independent variable is the time t. So we go from t, and the new independent variable is going to be the angle phi. And what do we have here? The dependent variable is r. Okay. We go from r to the reciprocal of r, which is lowercase u. Okay. Yeah, it's a remarkable transformation. What we want to appreciate, how do you change these variables? Okay. This is discussed on page 306. All right. It's a nice example of how we transform differential equations. And you know the result, right? The result is equation 841. This 1 over r is called u. And let's make an extra effort to make that u small. We must draw it small. This is a lowercase u, not to be confused with capital U. As it happens for the Kepler problem, capital U is a negative constant over r. So yeah, there's some similarity. But for this portion of the discussion, let's appreciate lowercase u has dimensions of inverse meters. Okay, that's the role, that's the identity, and we have a very clear definition. So in doing this, the crucial thing there is right between 838 and 839, we have the statement, we're going to change, you see the DDT operator. We're going to change that DDT operator, and we want to transform the equation in favor of a DD phi. Okay, so our point is to migrate. We do have this equation 839. Now, if you look at equation 839, there's quite a bit of content there. That equation includes several sub-transformations. In other words, there are multiple equal signs. Let's just summarize this equation. The equation 839 ddt is equal to, we got a cursive L, we got a u squared over mu, okay, dd phi. All right, this is the crucial thing with this equation 839. You see, we're changing the independent variable. How do you change the independent variable? Well, to differentiate something with respect to t means to form a difference quotient. If you look at the definition from calculus, what does it mean to differentiate something with respect to the time t? We consider a small excursion, a delta t. We form a difference quotient. The numerator is the change in the dependent variable. The denominator is our delta t. In the limit where delta t goes to 0, you have the derivative. Okay, so that's a clear prescription for what it means to differentiate with respect to t. Now, because we have a relationship between t and phi, right? Ultimately, phi is a function of the time t, and it's monotonically increasing in the region of interest here. So we can recast this in terms of derivatives with respect to phi. Okay, so originally we had this description of the problem, r as a function of the time t, and the end goal is we want the lowercase u as a function of phi. Okay, so we transform both the independent and the dependent variable, and here's where we get one of the central results, right? This solution, we can solve this, right? We recognize this as one of our equations from chapter 5, and we get the shape of the orbit. Okay, so this here gives you an overview of some very important themes, right? Differential equations are so important to us, the equations of motion, et cetera, and transforming the differential equations. So here in chapter 10, we have an example on the current homework assignment where you must transform, okay? If you're studying x as a function of t, right, we have x as a generalized coordinate, and we certainly have a statement about x double dot. How can you change that into a statement about s double dot? Okay, you're changing the dependent variable, okay, and you can review the techniques that were used here. This, in chapter 8, as you know, this is part of the most momentous, one of the most momentous achievements of classical mechanics, solving and showing that an inverse square force gives us these elliptical orbits. This transformation really was at the heart of it. When we had a difficult equation, we had this equation for r double dot at the top of page 306, very difficult equation, and we transformed it to a differential equation for u. We had second derivatives of u. This was essentially, apart from some minor tweaks, this was a simple harmonic oscillator equation, and the solution is that cosine that you see in the chapter 8 summary, right? In the chapter 8 summary, we have the shape of the orbit, r equals a constant, and downstairs you have, apart from some constants, that cosine of phi. Okay, that's the crucial thing. Of course, r is the reciprocal of u. So yeah, this is very important to us. Chapter 8 summary, very important to us. Okay, so that's an overview. And again, you see how all these things are related, changing differential equations. Here we got the generalized Snell's law, right? You remember this parameterization. The first optics discussion gave us a generalized Snell's law where we were looking at the gradient of the index of refraction. The gradient of the index of refraction serves to steer the ray. We're talking about a ray of light going through, for example, a slab of glass with a non-uniform index of refraction, or perhaps you're looking at a fiber. You're in Silicon Valley manufacturing fiber optic systems, and typically you do have these graded index of refraction components. Okay, so that's the key thing, graded index. All right, now we have a special treat today. We have a wonderful special treat. My daughter has brought the hamster, and the hamster's on the document camera. Okay, now the hamster, this is, though the hamster is small, it is a mighty hamster, and we're gonna do something special. The hamster is gonna choose a topic for the final exam. Okay, you know, a week from today is the final exam. Right now, it looks like the posterior of the hamster was sitting on chapter 13. That's not so cool. Hamster is going to choose a topic for the final exam. Okay, hamster doesn't understand. So here's what well, it appears he just wants to have fun. Okay, maybe that's the message. We're going to have fun on the final exam. We're going to have some really fun problems. I think that's, the hamster has spoken. The hamster has spoken, and it's going to be a feel-good exam. So look for lots of fun problems on the final exam. Okay, thanks, hamster. I was expecting him to sniff at this differential equation, or maybe that one. I was expecting a clear message, like the oracle. Anyways, okay. So yeah, a little bit of comic relief there. So yeah, and again, for homework 10, I did post the notes in the homework 10 folder. That should be helpful for the angular momentum discussion. So let's resume now. We're gonna work on closing out chapter 13, and then we're looking ahead to chaos, the fascinating world of chaos. A whole different world. We're still doing classical physics, right? Still classical physics, but much different results. Much different results. Okay, so let's make some closing remarks on canonical transformations. Right, and you know, as we were discussing canonical transformations, we certainly did transform some differential equations. So canonical transformations. Okay. We'd like to appreciate what's going on here, and quite generally, these are area preserving. So this is our first bullet. We're going to have a list of items here. They are area preserving. It is meaningful to talk about area in phase space, okay? And when we say area, we're thinking of a 1 degree of freedom problem where you have a 2-dimensional phase space. If you have more degrees of freedom, we're going to be in a higher dimensional space. And when we say area, it's going to be a higher dimensional notion, some sort of higher dimensional volume. Let's draw a picture for 1 degree of freedom. Here's lowercase q and lowercase p. So there's our phase space. And you know, when we talk about canonical transformations, we transform. We have a capital Q, that's our new Q variable, the coordinate type variable, generalized coordinate, and the conjugate momentum, capital P. Okay, so remember the canonical transformation. This is for 1 degree of freedom. Okay, 1 degree of freedom. There's a single Q, there's a single P, and so you have a 2-dimensional phase space. And the mapping here is the canonical transformation. Okay, so the canonical transformation is a mapping, right? We have capital Q and capital P as a function of the lowercase variables. You can think of that as a mapping. Any point in this space gets mapped to a point over here. That's precisely what those formulas tell you. So we can ask the question, what if you have a small area? I've drawn it as a small rectangle, okay? dq. There's a differential q here. And the reason I drew it as a rectangle is we have no meaningful concept of distance, okay? Q and P have different units in general, and we have no meaningful concept of distance. So it would be a little misleading if I drew a little square, because that kind of implies the edges are the same length. That's not cool in phase space, because in general, Q and P have different units. So I drew it as a rectangle, meaning they're different, okay? Here's a dp. So what's the area of this little rectangular patch? It's simply dq times dp. I'll put parentheses for extra clarity. Okay, now this mapping, it's a very general, it could be a nonlinear, there could be sines and cosines, that's what we saw recently. And so typically, this little rectangle gets mapped over here to something like this. Well, I should, let's draw it like this. I accidentally drew a vertical line. That would not be appropriate. It's a little parallelogram at some funny angle. All right. And so there's the differential area, and the statement is area preserving. It's unfortunate I drew that too big. Now I got a problem. What am I going to do? There's no easy way to fix this right now. Just verbally state that these two are supposed to have the same area. Okay, so that's true quite generally. If you have a point, let's have this be, you see I'm emphasizing the lower left corner. That's a point QP in the space. Then we have a DQ that takes you over here and a DP that takes you over here. Let's say that point got mapped over to here. Capital Q, capital P right there. And these two differential excursions giving you nearby points, they get mapped over here like so, right? So it's meaningful to talk about this, and these mappings are area preserving. Now there's something special that happens. You know from your studies of complex analysis, there are times when you study functions of a complex variable and you talk about functions that preserve angles. It's especially interesting to talk about the 90-degree angle, okay? Oftentimes in the theory of a complex variable, you'll talk about functions that preserve angles, and that's completely different. I just want to mention that's a different topic. If you want to talk about angles, again here, in phase space, there's no meaningful way to talk about angles. We can't really talk about the angle between two vectors, right? The most common way to compute the angle would be to get the dot product, et cetera, solve for the cosine. We can't do that here. So although there are some similar theorems in the theory of complex variables, let's appreciate that this statement is fundamentally different in 2 dimensions. Okay, and this is a 2-dimensional example. If you have 1 degree of freedom, it's a 2-dimensional phase space. Area preserving is identical with a canonical transformation. So an area preserving the concept of being area preserving is equal to, it's identical to being canonical. Okay, and that's important to us. You remember, again, we're not going to prove this. We just want to appreciate some of these statements and appreciate the geometry here. You remember, we looked at a very specific example of a canonical transformation. Okay, we had a transformation that resembled good old plane polar coordinates, right? The plane polar coordinates are manifest in much of our work because we often use cylindrical coordinates in 3D. And then the XY space is getting transformed according to plane polar coordinates. We have the distance from the Z-axis and a certain angle relative to the X-axis. So if you look at plane polar coordinates, they're not area preserving. It's necessary to incorporate that square root. Remember, we had a certain square root, and let's get that square root here. So, So remember, we did a very interesting calculation. We had these matrices. I'm just looking at some notes from a recent lecture. And there you have it. It was this transformation here. Notice how we had the square root of 2p. That was necessary to make the transformation area preserving. Okay, and if you go through the details of the calculation, you see it is area preserving. And so that's useful in 2 dimensions. If you have an area preserving mapping from one 2-dimensional space to another, then it's a canonical transformation. You can use that immediately to transform Hamilton's equations. Okay, now let's move on to our next subject, and this again relates to homework 10. The current homework assignment, homework number 10. Okay, Poisson brackets. If you have had quantum mechanics, you're familiar with Poisson brackets. It's okay if you have not had the quantum mechanics. I'm referring to the 137 course. Poisson brackets. Okay, So let's appreciate what's going on here with Poisson brackets. Okay, there's a question here. I'm looking at the chat window. So Hamilton's equations are invariant. Yes, that's a good point. Canonical means Hamilton's equations are invariant. Yeah, that's an excellent point, and that's why it's important to us. So Hamilton's equations okay, and so I'll write it like this. Yeah, as you point out, Hamilton's equations are invariant. And I want to emphasize, what does that mean? Hamilton's equations are invariant. Well, if you write out, what is capital Q dot? Capital Q dot is equal to the transformed Hamiltonian differentiated with respect to P. Okay, so that's the same structure. It's what you have in the chapter 13 summary. You have this pair of equations. The Q dot is a partial derivative of the Hamiltonian with respect to P. The P dot is -1 times the partial derivative of the Hamiltonian with respect to Q. Yeah, and so the remarkable thing here is when you transform to the new coordinates, transform the Hamiltonian, you still have this structure. Yes, absolutely. So that's a very important observation. This is the definition of canonical. Hamilton's equations are unchanged in form. Okay, Poisson brackets. Here's an opportunity to emphasize our understanding of the mathematical structures that we're working with. If you have two functions on phase space, so consider okay, so we have this lowercase f and lowercase g, functions on phase space. So in this example, with 1 degree of freedom, phase space is this two-dimensional space like so. And f, this is a scalar function. That means that every point in this diagram, you have some value for f. For example, f could be the total mechanical energy, right? We know the total mechanical energy is a function of the classical state. So every point in this picture defines a classical state, and you have some total energy. So that's an example. Lots of other examples, kinetic energy, angular momentum, etc. Even Q itself. Q is certainly a function on phase space. That means at any point, you simply record the Q value, you ignore the P value. That's a well-defined function on phase space. So that's our first installment here. We have several foundation mathematical concepts, right? The structure, the mathematical structure, and this is part of the mathematical structure. We're talking about functions defined on phase space. So the Hamiltonian would be another nice example, right? Okay, so that's the first thing. Here's a prescription. This now is the definition of the Poisson bracket. Okay, the Poisson bracket is defined with these curly braces, but let's emphasize this is simply notation for a mapping. So I'll write out the definition, but you could have, let's note. It's simply a mapping. You provide two functions defined on phase space. It gives you a new function defined on phase space. So we could have simply called it P sub B, right? If you look at the letter Poisson bracket, let's just name the function PB. It is a function that takes two functions and gives you a new function. Right? All right. So the emphasis here is that this is a mapping. So let's just emphasize this is a mapping. Okay. We use the word mapping to indicate kind of the most general notion of what it means to be a function. We've talked about differential operators. You remember in chapter 5, we had a differential operator, capital D, which involves second order differentiation, second order time derivative. And that's an example of a mapping. You could call it an operator, etc. So this is a mapping. So more conventional notation, right? Typically, if you have a mapping, we like to write it like this. The arguments, that's the input information. So this is a mapping, it's a prescription. You provide some input information, it provides some output information, which in this case is a new function. All right. So historically, people use these curly braces. So that's just fancy notation for, again, this notion of a mapping. All right. So let's write down the formula and convince ourselves this is a mapping so that we're going to sum. We're summing over all of the degrees of freedom. So lowercase n is the number of degrees of freedom. Okay. And here's a prescription. We're going to compute some partial derivatives, and then the grand total is the output information, which again is a function defined on phase space. So we're going to compute a partial. Okay. So you see this is a prescription. It tells you exactly what to do. If you have two functions, f and g, whatever they may be, arbitrary, they don't have to be the solution to anything, just two functions defined on phase space. Then this tells you start computing some partial derivatives. We need all the partial derivatives of f with respect to q, all the individual q's. We need all the partial derivatives of f with respect to p, and the same is true for g. Here's partial g, partial pi, partial g, partial qi. So this is a peculiar combination of all these partial derivatives. Okay, it's a very peculiar combination of partial derivatives. It's kind of reminiscent of the curl in the sense that the curl of a vector field, right? You provide a vector field, the curl is a prescription, and it provides a different vector field. So the difference is when we talk about curls, we're talking about vector fields. The similarity is the curl is there's a very clear prescription, especially in Cartesian coordinates. If you have a vector field, you must compute some partial derivatives, and then we will concoct kind of a crazy combination of all these partial derivatives with some bookkeeping, right? There are plus and minus signs. So the curl of a vector field is a prescription where the input information is a vector field. That's a field defined on a three-dimensional space. It must be three-dimensional. And the curl is a prescription. You follow the recipe, so to speak. You compute some derivatives. You have some bookkeeping with plus and minus signs. The resulting object is again a vector field. So that's the similarity. A difference would be the curl. You just have a single vector field as the input information and a single vector field as the output information. But the similarity was you compute a bunch of partial derivatives. Okay, here you have two scalar fields. These are not vector fields. F and G are scalar fields. This construction here asks you to compute a bunch of derivatives, bunch of partial derivatives. In this case, we're going to add them up, etc., with proper minus signs in place. The resulting object is, again, a function on phase space. So that's the crucial thing. This object, the output function, this new function is, again, So this, this is the construction. Again, the notation is funny. Now let's observe there are some similarities to quantum mechanics, right? In quantum mechanics, you have the so-called commutator. And the commutator, if you have had quantum mechanics, right, this is an optional remark for those of you that have had, the, for example, Physics 137. The commutator, you have these kind of square brackets, right? So the notation you see is reminiscent. And there's a deep connection between the classical Poisson bracket and the quantum mechanical commutator. Now the commutator, what we're doing there is we have two operators. If you have a basis, then of course you can express the operators as matrices. And there, we don't differentiate them. We simply work out the matrix product, F times G, then with the minus sign, G times F. Okay, that's the commutator. Very important in quantum mechanics. And you'll see when you study the relationship between classical physics and quantum physics, you probably, if you have had the quantum, you know that if you work out the commutator, Lx, that's the x component of angular momentum, with Ly, right? So the commutator, again, Lx is an operator, Ly is an operator. If you have a basis, you can express these as matrices. And we're talking about multiplying the two matrices in one order. And in general, matrices don't commute. So when you switch the order and work out the product, you get something different. The difference is precisely the commutator. If the commutator is 0, then the matrices are said to commute. And here, if the Poisson bracket is 0, the two functions are said to Poisson commute. Okay, or you can just say there's a vanishing Poisson bracket. Okay, so yeah, it's interesting to observe. And when you study the relationship between classical physics and quantum mechanics, there's a deep connection between the Poisson bracket and the commutator. Okay, now what we're going to do next is just rewrite some results that we already know using Poisson brackets. Okay, so the results that we're going to get are not fundamentally new. We're just writing them using some new notation. Okay, so here's kind of the cool thing about the Poisson brackets. Let's do this. We're going for, yeah, let's do it like this. So you see the continuity. We're continuing this discussion here. Okay, now notice Qi dot, so that's the total time derivative of Qi, is equal to, well, according to Hamilton's equations, that's a partial of the Hamiltonian with respect to Pi. Okay, and let's observe, that's the Poisson bracket of Qi with the Hamiltonian. Okay, so why is that true? Well, let's contemplate, what is the Poisson bracket of one of the Q's? So this Qi now, this is a so-called free index, right? If it's just sitting there like that, it's a free index, meaning whatever we're gonna do here, it must be valid for I equals 1, it must be valid for I equals 2, dot, dot, dot. It must be valid for I equaling little n. So in that sense, this is a collection of statements. It's true for any concrete specific choice of the index I. Okay, so with that in mind, think of I as some index, for example, 4. You know, it's some fixed value of the index. So for this lowercase f, we're going to think of, for example, Q4. Okay, what happens when you start computing all these derivatives? Well, remember the Q's and the P's are independent variables. Okay, the Q's and P's are independent variables. So when you, and again, we're thinking of this f as Q4, for example. Then over here, all of these partial derivatives are 0. The partial of f with respect to any p, that's 0 because q's and p's are independent variables. So all these are 0. And here, there will be precisely one term that's non-zero because all the q's are independent variables. It's when this index, which here is a dummy index, right? That's a little bit unfortunate. Here, I is a free index, but because this is just a single sum, we can do this in our heads. Imagine renaming this index to j. So we're summing j from 1 to n, and these things are all j's. Well, when j is equal to I, this partial derivative is equal to 1. Otherwise, the partial derivative is equal to 0. So it's precisely when j is equal to I. So again, we're thinking of this as being something like Q4. Then when I is equal to 4, that's the only non-zero term, and the only term in the answer is the partial of the Hamiltonian with respect to P4. Okay, that's precisely what we're saying here. So you see, this is one of the two Hamilton equations, and it can be written as a Poisson bracket. All right, next. We have another one of Hamilton's equations here. The total time derivative of Pi is minus okay. Let me just fix my notes here. And here's some good news. You don't have to worry about the minus sign. The Poisson bracket takes care of that for you. Now, a moment ago, we verified the Poisson bracket for this one. Again, the same logic goes through here. The minus sign will save the day in the definition of the Poisson bracket. And so, remarkably, this is true for any function on phase space. If you have an arbitrary function on phase space, oops. I was thinking ahead to the notation, so I accidentally wrote a G. Let's call this an arbitrary function A. So A as a function of the Q's and P's. All right. If you have an arbitrary function of the Q's and P's, you can consider the total time derivative. What does that mean, the total time derivative? All right. The total time derivative of an arbitrary function, this means we think of some solution. So now Q, all the individual Q's as a function of time, we're thinking of that as a solution, the time evolution of the system, and all the P's as a function of time. We have the time evolution of the system. And you construct with functional composition a capital A as a function of just one variable t by inserting the so-called orbit in classical mechanics. That's the solution Q of t and P of t. So in that sense, we construct a capital A that's a function of t only. And this is what it means to compute the total time derivative of anything in classical mechanics. This is equal to the Poisson bracket. All right. And you have similar results in quantum mechanics. I won't do a whole bunch of quantum today, but there are similar things in quantum mechanics with the Poisson bracket with the Hamiltonian. Okay, so for what we're doing, we just want to appreciate that Poisson brackets exist. We want to understand how to compute a Poisson bracket and observe, just kind of take it on faith. This is a springboard to a whole bunch of topics that are of interest in classical mechanics. The so-called Poisson bracket formulation. It's equivalent to the Hamiltonian formulation, Poisson bracket. So the folks over in the math department, you know, they love to consider different mathematical formulations of mechanics. And so the existence of this Poisson bracket, and there are other things like the so-called symplectic form. When you take Physics 205, you'll talk about the symplectic form. There are different kind of mathematical structures, bilinear forms, things like that. Okay, so that's the extent of our interest for this one. So let's move on to our next topic here, Louisville's theorem. And this is where the Hamiltonian formulation of classical mechanics really shines. We have a very important theorem here, Louisville's theorem. You see all these names are French. I guess the French truly appreciate classical mechanics. Can I spell this correctly? Okay, so for Louisville's theorem, and I mentioned the applications, right? Several years ago, I was working with a lot of people at Lawrence Berkeley National Laboratory. We had a huge team working on the design of a next generation light source. And here you must think about a so-called bunch of electrons. That could be a nanocoulomb, for example, about 2 billion electrons moving through a large machine. And you want these electrons to be as close as possible together in physical space, but also close together in momentum space. What does that mean? That means their momentum vectors should be close together. Okay, so we're in a higher dimensional space and we're talking about a certain density. So imagine you have a collection of particles here. So here's a collection of particles. I'll draw a single Q axis and a single P axis just to convey the notion that this is a phase space. And let's talk about time evolution. Suppose, and I'll use this curvy arrow, time evolution. So I'll just write the letter T for time evolution. So here at some initial time, you have all these particles. I drew a bunch of dots. There they are at some initial time. Some time T later, let's say they're over here. And there we go. That's a pretty good blob of particles. Okay, so this is the time evolution of these particles. So here's the statement. The phase space volume. Remember earlier today we talked about area. That was special, a special state of affairs for 1 degree of freedom. Really the most general case is a phase space volume. So the phase space volume is constant under time evolution. So I'll write it like this, equals constant under okay. So what I had here, originally I drew a certain blob of particles. It quote looked like a circle. Of course, we can't really say it's a circle. Oh, we got a little internet slowness. Yeah, we got some internet slowness. That's unfortunate, but we're going to make it through. I can tell because my document camera is sluggish at times. Okay, so here's a blob of particles. Later, the shape of the blob of particles may be different, but the volume is constant. So you see how this blob of particles, it's narrower going across like this, and then it's elongated like so. The total phase space volume is a constant under time evolution. So that's important, and that's why you often hear people talk about Louisville's theorem. You may be attending a meeting with all these wonderful physicists, right? The so-called accelerator, well, the terminology that's used, accelerator physicists. The team is called the Advanced Light Source. I think the physics team. Anyways, yeah, they're often talking about the phase space volume, and they'll mention Louisville's theorem. So in our next meeting, we'll investigate how can you prove that the phase space volume is constant under time evolution. The shape of the volume, it could get, one speaks of filamentation. If you truly evolve this picture, if this T is large, these particles could be moving all over phase space, and what originally was kind of a blob, it becomes filamented. So you have these thin kind of protrusions like tendrils all over the place, kind of looking like an octopus, or more bizarre than that. That's possible, but strictly speaking, the phase space volume is constant under time evolution if it's a Hamiltonian system. All right, so that brings us to the 2 o'clock hour. As you know, on my to-do list, I'm going to look at the syllabus. I'm going to rewrite the part about the grade because as stated here in the chat window, and I do save the chat window, there was a private message to me. We would like to update the syllabus concerning the grading philosophy. So this, of course, is an important issue for some students, and looking ahead to other schools. If you're going to attend another school, we have to have a statement about the grading philosophy. Okay, so that's on my to-do list. I'm going to stop the recording. I will stay here. Let's click on stop, and I'll stay here for questions.